Hi everyone, welcome to this episode of Kuipert Labs. We're going to be talking about, so it's titled, Hydronium, hydroxide and the self-ionisation of water. We're going to start, with this video, we're going to start heading towards developing our understanding of pH and its relation to acids and bases and what it tells us, and how we can calculate and work with the pH scale as a measure of acidity. But we're going to start by talking about something curious. Okay, so now let's have a quick look at our water molecule. Okay, so we know that our water molecule looks something like this. Actually, if I'm to be a little bit more honest, it looks a bit more like this, with two lone pairs on the oxygen atom. Okay, so each lone pair kind of taking up some space to give it a bent shape with tetrahedral geometry. If you remember back from year 11, thinking about the fact that we've got four things around our central atom, and so then extending out in three dimensions that way. And but what we know, aside from now looking like I've drawn a really bad bumblebee or something, is it's a covalent molecular compound. Okay, so it's not ionic. It's not ionic, but it's covalent, and it exists in these separate discrete molecules rather than as one big network of atoms connected all together. So it's covalent molecular. Now the thing that's interesting is so that it's molecular, so it's not made up of charged particles, like sodium chloride or anything like that is, but that what we see, if we take a beaker of water and we stick in some electrodes and then we monitor what happens with a voltmeter, or maybe we're monitoring the current or something like that, what we see is that we do get a small but noticeable conductivity. That is, it does conduct electricity even when it's highly pure. Much more so than other covalent substances that you might expect, like chloroform, which is CHCl3, or hexane, C6H14. They're covalently bonded, and with much bigger molecules, but they don't do this like water does. And so it's curious for us trying to work out exactly why. And the answer kind of comes back to what we've been learning about with the Lowry-Bronsted theory, is that we recognize that when we're thinking about acids and bases, that water isn't necessarily the impartial solvent that we've been making it out to be. That actually, every now and again, when we get two water molecules that are near each other, and certainly in a container of water there's many of that, once, maybe like, a millionth of the time, one in every 10 million times that we get this happening, that we get a transfer of a proton from one water molecule to the other to form hydronium, a hydronium ion and a hydroxide ion. Okay, in equal proportions, as far as for every one proton that's transferred, we get one of each. Okay, now so this is something that we say is the self or auto-ionization of water. That is, it's actually able to become ionized by interacting with itself, with other particles of itself. That partly comes back to our structure that we kind of looked at, the fact that our oxygen, our oxygen has these lone pairs of electrons, that then if a hydrogen happens to be attracted strongly enough to one of those lone pairs of electrons, that then it can actually be pulled off to attach onto that to make a hydronium, and leaving behind this relatively stable hydroxide ion. Okay, we know that these two ions can react together to go back and form water. So in reality, we should draw that as an equilibrium to be a bit more precise. But so what that means is that whenever you get a pure sample of water, that you actually have a very small proportion of ions, even if you didn't dissolve any to start with. Even if you could guarantee that there was 100% water molecules in there to start with, after some time there'd be a small but not negligible amount of hydronium and hydroxide. So if you're kind of keeping keeping tabs on relative amounts, you end up with stacks of water molecules, and then maybe you've kind of got a tiny proportion of these two ions in that same solution at the same time. Okay, and so that means that it is able to conduct electricity. But what we see something really curious is that when we get to water that's around about neutral, that we get concentrations. So our hydronium concentration is at about 1 times 10 to the minus 7 moles per litre, and so is our hydroxide. Okay, so that's why it's really, really small. It's much, much smaller than the concentration of water molecules around it, but there's not nothing. Okay, and so these are in moles per litre. But what we notice is that if we add in other substances to kind of bump this up, so we add in hydronium ions, say we take it up to 10 to the minus 6, we've increased it by a factor of 10. What we see is that our hydroxide ion concentration goes down. I'll draw these a little bit larger for you just to make it a bit easier to see on camera. Okay, so if we've got, say, 1 times 10 to the... So we've now got 1 times 10 to the minus 6, and we've got 1 times 10 to the minus 8 moles per litre. Okay, and then let's say we do it again. What happens is, we go up with our hydronium. What we notice is that our hydroxide goes down proportionally. Okay, and we can go 4, 10, and we end up with minus 10, and so on and so on. And say we even get to the point where it's 1 times 10 to the minus 1, and we end up with 1 times 10 to the minus 13 moles per litre for hydroxide. So we see that as one goes up, the other goes down. And it goes down, and it's proportional. Okay, remember that we've used this kind of language. I'm just drawing symbolically at this point, I know. But so what we would say, so we use this term inversely proportional to each other. That is, as one goes up, the other goes down. Okay? And so what we notice with that is that we see a specific mathematical relationship here. We don't see anything particularly mystical about it, even if it's an interesting sort of relationship to notice. So what we see is that, okay, we've generalized the pattern out to say that, all right, if I take the concentration of the hydronium ion, and that's what this kind of bracket notation means, just so that you're aware. If I take the concentration of hydronium at any conditions, and I multiply it by the concentration of the hydroxide ion, I get a constant number. Okay, no matter what concentration I have here, if I multiply it by the concentration we can measure here, I end up with this number specifically, 1.0 times 10 to the minus 14. Now it's a constant, it's not a measure, it's not a unit of measurement, it's a constant number. And so what we see is if no matter what I plug in here, whatever I measure of the hydroxide and I multiply those two things together, I get this value. And we give this constant a name. We give it capital K with a little w. Okay, so what we see is that we saw before that we had an equilibrium between hydronium and hydroxide and then water molecules. When we're thinking about equilibrium, and we can, if we were doing industrial chem, we would do this, we can actually calculate mathematically, make calculations using a constant value that relates to equilibrium called K. So that's where this kind of kicks in. We just kind of neglect to touch on the rest. But the idea is that we can use this number to make calculations. If we know one of these two things, we can work out the other. Okay, and so so this is the ionization constant for water. So let's look at this kind of relationship. So say I had a hydronium ion concentration of 0.015 moles per litre. Okay, and then I wanted to find out my hydroxide concentration. So I could say, all right, so 0.015 multiplied by x is equal to this constant value. And so therefore, x is equal to that constant divided by 0.015, and then we can do the calculation from there. Okay, and so we can work out exactly how much we would have at any particular situation. Okay, and so it's a really interesting maths relationship that we can use, and what it does is it forms the basis of what we will then look at now as the pH scale, because we're able to use this relationship of how these concentrations change in particular solutions to then say, okay, well, we can use this and measure this and then make calculations to know exactly how much hydronium, how many hydronium ions, what concentration we have in that solution, and therefore how acidic it is. Okay, so that's for a future episode. All right, thanks very much for watching. Bye for now.